Okay, now let's see how are we going to solve it. Okay, oops. Yeah. Okay, now it's coming out. Okay, let's see. What are we going to do in this subtopic? Now you have a gravitational potential energy. In previous lessons, we have discussed about this topic a little bit. So today I'm going to discuss a bit more with you. Okay, just do a quick revisions. So first of all, what does it mean by gravitational potential energy? Now we know that every mass it can be attracted towards the other mass, right? Now, first of all, we need to know, okay, now every mass it comes with a field, all right? And if you place another mass within this field, then both of them they will experience gravitational force. If you place it outside the field, then it won't feel anything. So gravitational energy, it just simply means that now you're moving this mass from outside the field into the field. So what is the energy needed to place that at a distance of r? Okay, so the distance again should be from the center to center. All right. So you want to place them at a distance, let's say 10 meter apart from each other. So how? Okay, what is the energy needed? So this is from the initial position. Now you want to place it. This is initial position, which is from infinity. So you want to place it inside the field, okay, so that it's located at a distance that is r from the point mass. So the main mass, okay, the mass that's initially at the system, which we call it point mass. And then this one, we call it test mass because you move it around. You move it from outside into the field. You move it around. You test the value. Okay, you get a value from moving it. All right, and then what else do we have? Okay, now this is an infinity. Okay, from infinity to place it at the locations that is r from point mass, we need to calculate the work done needed, which is U equals to negative GMM over R. This is the amount of work needed to do from bringing it from an infinity into a field, okay, around the point mass. What if the object, the mass, is already inside the field? Initially, it is already inside the field at positions 1. Now you move it to positions 2. Okay, you move it to positions 2. So both position, okay, both initial and final positions, they are located inside the field. So now what are we going to calculate? We want to calculate the work done in bringing it from positions 1 to positions 2, not from infinity into a point r anymore, okay, into a distance r anymore. Now it's already inside the field. So what are you doing? You are just bringing it from positions 1 to positions 2. Therefore, there is a change in gravitational potential energy. So we want to calculate the work done. Okay, the work done in bringing it from point 1 to point 2, which is U final is 2 minus U1. So if you expand these equations, eventually you're going to get negative GMM 1 over R2 minus 1 over R1. So that is the main difference between these two scenarios. One is you bring it from infinity into the field, therefore you have just U equals to negative GMM over R. Another one is you move it from one position to another position inside the field. Then you need to use final U minus initial U in order to calculate its value. All right, in order to calculate its value. All right, next. Now let's look at these questions. Okay, let's solve it. Questions 1. Determines the gravitational potential energy of the Earth due to the moon only and the sun only. So what is the energy needed to place the Earth or to make sure the Earth is located at a distance that is 3.84 times 10 to the power 5 km from the moon? So you want the distance between moon and Earth is 3.84 times 10 to the power 5 km. So what are we going to do? We just simply apply the equations. U equals to negative GMM over R. Because you are not bringing it from outside. Okay, you're not bringing it from inside, from one point to another point. You are bringing it from outside. And then you place it at a position so that the distance between Earth and Moon is 3.4 times 10 to the power 5 km. So U is equals to negative GMM over R. Now you have to be extra careful with the unit given. Unit given here is meter, okay? But then the other one given is km. So you yourself need to convert everything into meter. Okay, need to convert everything into meter. Therefore, you have negative G, which given is a 6.4 67 times 10 to the power of negative 11 times with the m. Now, you're going to calculate potential energy between Earth and the moon. Okay, the Earth and the moon. So you need to use the m for the Earth and the mass of the moon. So mass of the Earth is me, which is 5.98 times 10 to the power of 24. And then this one I have 7.35 times 10 to the power of 22 divided by the R. Okay, so R between the Earth and the mass is 3.84 times 10 to the power of 8 because you have a K here. Okay, K is times 10 to the power of 3. Therefore, it becomes times 10 to the power of 8. So you're going to get U is equals to negative 7.63 times 10 to the power of 28 joule. All right. So this is the work done. Okay, the work done needed to place the Earth and the moon. Okay, at a distance 3.84 times 10 to the power of 8 meter between each other. So initially the system is empty. All right, the universe is empty. So you place a moon in the universe and then you spend an energy and work done that is equivalent to negative 7.63 times 10 to the power of 28 joule to place the Earth into the universe as well. So you place both of them into the universe by spending this much of energy. Okay, by spending this much of work done, by doing this much of work. And now the B. Okay, B is for the sun and the earth. So basically, you're just going to repeat the same thing. So I will leave it to you. Okay, you yourself try to complete it, calculate it, and the answer should be equals to 5.32 times 10 to the power of 23 joule. All right, so this is the work done needed to place the sun and the earth, two of them, into a same universe. Okay, which is inside the field of each other. Okay, so now I give you 2 minutes to write down the answer as well as a brief summary, a brief revision just now. Okay, so make sure you know what is the difference between these two scenario. Okay, so if there's anything you don't understand, make sure to ask, yeah? Because today we're just going to focus on the gravitational potential energy. All right. Okay, so this is a very simple questions. Now let's look at the next questions. Okay, so let's look at the next questions. Next questions. We have if a set, oops. If a satellite of mass 800 kg falls from a height at 400 km to the surface of the Earth, what is the loss in gravitational potential energy? Now you don't just look at gravitational potential energy. The key word is the loss. So what does it mean by loss? It means you are going to look at delta U. Okay, you are going to look at delta U. That is what the questions want. Not just gravitational potential energy, but actually it's asking for the change in gravitational potential energy. Now, first of all, you need to understand the questions. If a satellite of mass 800 kg falls from a height at 400 km to the surface of the Earth, so what does it mean? So now you have the Earth, and then this is a satellite. Okay, this is a satellite. Initially, okay, this is the initial position. Initial position, the satellite is located at 400 km. Okay, 400 km from the surface of the Earth. But then you don't forget about one thing. In chapter 7, when it comes to calculations, the R that we're going to use is from the center of the mass. Okay, this is the R in our calculation, in which it means if you want to calculate the gravitational energy for the satellite that is located at a position that is 400 km above the surface of the Earth, then you need to add the radius of the Earth. Okay, which means at initial position, R is actually equals to capital letter R plus 4 times 10 to the power of 5 meter. Okay, times 10 to the power of 5 meter, because it's km again. So you need to change it into SI unit. And then what happened? It tells you now the satellite drops. All right, the satellite drops. And then what does it drops? So now you still have the Earth. Okay, and now your satellite, it drops to the surface. Okay, it drops to the surface of the Earth. So what does it mean then? Now it means the radius or the distance, the R that you're going to use is just the R of the Earth, the radius of the Earth. All right, so this is the final position. Final positions, your R is actually equals to capital letter R, okay, or RE, according to the values given, okay, the variable given, they call it RE. So we call it RE as well. So you have a mass ME and then the mass here ME. And the mass of satellite given is 800 km. So I'm just going to call it MS because it's a satellite. So MS, satellite. Okay. So next, since question is asking for delta U, so delta U is equals to negative GMM bracket 1 over R final minus 1 over R initial. Okay, so negative, well, I'm going to keep GMM. So you yourself substitute the value and solve it. So GMM bracket 1 over, now R final is just RE. Okay, it's just RE minus, okay, 1 over R initial. So R initial is RE plus 4 times 10 to the power of 5. Okay, so this is your equations. Then you sub the value of G, M, and RE into the equations, and eventually you will get negative 2.95 times 10 to the power of 9 joule. So this is the final answer. All right, this is the final answer. So that is how you solve the questions. Okay, so I'm going to give you 2 minutes to write it down before we proceed to next questions. Okay, try to calculate, and I want you to sketch the diagram. Okay, now I'm going to give you more minutes. Okay, you try to sketch the diagram. Okay, make sure you sketch the diagram because I want you to see what happened. Okay, and especially in terms of R, because this is a very, I would say, is a very common sense trap in your exam. If you got the wrong R, then basically the whole question is going to be wrong. Why? Because almost every equations in chapter 7, okay, you need to use R. So if you don't know how to get the right R, how to calculate the correct R, then basically you won't be able to answer the questions in chapter 7. Okay, so R always from the center of the mass. So sketch the diagram and then solve the questions. All right. So I give you until 20 past 12. Okay, lukis diagram. Saya nak kamu betul-betul faham, nampak di manakah kita kira R. Macam mana kita dapat R berlainan. Okay. Hope you can understand. Okay, so let's look at the next questions. So the moon has a mass of 7.35 times 10 to the power of 22 kg and a radius of 1740 km. So once again, you have the unit in terms of km. So in this chapter, you have to be extra careful because the distance that we use is a very large. Therefore, the unit usually is not in terms of SI unit. Okay, so you yourself need to convert it into SI unit. So determines the gravitational field strength at its surface. So you want the gravitational field strength. Now, what does it mean by gravitational field strength? It's Ag. Okay, it's our Ag. So Ag equals to Gm over R squared. Since you are looking at the field strength at surface. Okay, so at surface means you're just going to use a radius. Therefore, it is 6.67 times 10 to the power of negative 11 times with the mass, which is 7.35 times 10 to the power of 22, divided by the radius of the moon. So it's a 1740 times 10 to the power of 3. So you will obtain 1.62 Newton kg negative 1. So of course you want to use the ms negative 2 also can. All right, it is up to you. So that is the questions A. Now questions B is very similar to previous question. And now it uses the terms change in gravitational potential energy. So this is things that always overlooked by students. Okay, there's a term called change in. So it's asking for, again, delta G. All right, not just G, but delta G. So a probe of a 100 kg is dropped from a height of 1 km. So now you have a moon and the probe is located 1 km above the moon. So again, you have here is equivalent to 1 km, but you have to recall that in order to calculate the potential energy, you need the R from center. Okay, you need the R from center. So this is your initial positions. So initial positions 1, again, R is equals to R moon plus 1 km. Okay, plus 1 km. So which is 1 times 10 to the power of 3 meter. And the final position, because it says it drops, okay, it drops onto the moon. So which means the final position is just on top of the moon. Okay, therefore the R is straight away equals to your R moon. Okay, your R moon. So R M. So final R is just equals to RM. Okay, so initial you have RM plus 1 km. So how to calculate it? Same as previous questions. Okay, same as your questions 2. So start from delta U equals to negative GMM. Okay, bracket 1 over R final minus 1 over R initial. And then equals to, okay, you plug in the value and then you will obtain negative 1.62 times 10 to the power of negative 5 joule. Okay, times 10 to the power of negative 5 joule. So now I'm going to give you 2 minutes to write down questions A and B first before I proceed to C. Okay, you solve it, you complete the questions. Okay, you complete the answer. So make sure everything is complete, all right? Because we have done discuss it, don't leave it blank. And then make sure to write down the diagram as well. The diagram is very useful. Okay, without diagram, sometimes when you do revisions, you don't know what does it mean. Okay, catat semua ya, catat semua. Okay, I'm going to do a next question C, and perhaps I will do a chapter exercise 4 as well. Okay, because if you got extra times, I want to use it to discuss your UPS questions. Okay, UPS questions. I think got quite a lot of you who score less than 50%. Okay, now let's proceed to the next questions. Question C. Now, question C. Okay, it's what I would say is a tricky questions. Why? Now it tells you what? Oops. It say if all the gravitational potential energy loss is converted to kinetic energy, then calculate the speed at which the probes hit the surface. So how are we going to calculate? Now try to think. energy cannot be created or destroyed. All right, it can only be transformed from one form to the other form. So which means, because you say or, which means delta U is straight away equals to your delta K. Okay, delta U is equals to your delta K, but then we just ignore the negative sign. Okay, so what we want is just 1.62 times 10 to the power of negative 5. Okay, because that is the amount of energy that's being converted. You're not going to look at whether it's positive or negative. We just want the magnitude. So delta U is equals to delta K, and delta K, what does it mean? It means K final minus K initial. All right, K final minus K initial. Well, again, it uses the terms drops from a point that is 1 km above the moon, which means initially the V is equals to 0. Therefore, our K initial is equals to 0. All right, so what is left in the equation is that K final is straight away equals to 1.62 times 10 to the power of negative 5. Okay, 1.62 times 10 to the power of negative 5. So 1 over 2 mv squared is equals to 1.62 times 10 to the power of negative 5. So plug in all of the value, you will get V is equals to negative 56.92 ms negative 1. Now, why negative? Because it's dropping. Okay, because it's dropping. So if it is dropping, then of course the direction is pointing downwards. But then if you look at the questions once again, it's asking for speed. Therefore, you rewrite the answer. Okay, the speed is, okay, in terms of a positive value, 56.92 ms negative 1. All right, 56.92 ms negative 1. So the crucial part is whether you understand this or not. All right, because it says all of the gravitational energy is being converted into kinetic energy, and we know energy is always conserved. Okay, so total delta U is equals to total delta K. So from there, you then calculate the final speed. All right, now I give you 2 minutes to write it down before we proceed to exercise 4. Okay, kalau ada soalan boleh tanya. Kita dah siap dah. Okay, we're done with gravitational potential energy. Okay, again, let's move to next. Ooh. Okay. So next, use escape velocity. Now, escape velocity is very simple because it starts from a conservation of energy, which we have been discussed in the tutorial. So we know that when it comes to the escape velocity, if it is escape from the outer space, okay, escape from far, okay, in other words, so then we have a VE, which is equal, V small letter E, sorry. Escape velocity, the subscript will use small letter E, okay, E represent escape. So if you just write V, then that is not escape velocity. That could be your initial, that could be your final, okay. So VE is equals to square root 2gm over R. So this R could be any R, okay, this R could be any R. So it is at any point, okay, at any point, at any position in the outer space. Okay, in outer space. But if you are going to look at the surface of the earth, okay, for example, now in the if the test mass for you, or for example, you yourself as a human who is standing on the earth, if you want to escape, okay, if you want to escape from the gravitational pull, then the speed, okay, the speed is going to be square root 2 gr, okay, square root 2 gr. So this is on the surface, okay, on the surface of the earth, okay, on earth's surface. Okay, to make it easier, we just say on earth's surface. So this r, I'm going to use re, then it's on the earth's surface. Done. So basically just two equations. And if you notice, when you look at these two equations, we don't need any information about point mass. The mass that we're using is just a mass, you see, capital letter M, capital letter M, and capital letter R. All right, it's mainly focused on your point mass. So as long as you know the point mass, for example, the Earth, or you want to escape from the Mars, from a Pluto, then you just need the information of the planet. Okay, then you can calculate the escape velocity. So two equation, one for any positions and another one is for on the surface. So if you are looking at the Earth, then R is RE. Okay, if you are looking at the moons, then it will be RM. So basically this equation, the second equation, is for object that is located on the surface. It could be on any planet surface. Then you just change the R that you use and also the G. Okay, and also the G. So G here must be G of the Earth, which is 9.81. All right, now calculate the escape speed from the Earth's surface for a rocket of mass 3000 kg. So this first question is a very, very, very tricky question. Okay, now if you notice what I just explained, I say you don't need the mass of rocket, but then it gives you a rocket of mass 3000 kg. So they want to trap you. Okay, so questions A, actually you don't need this. Okay, you don't need it. What you need is just V escape equals to, okay, you can use either equations. Okay, so since we are now looking at the object on the earth, let's use the second equation. So square root 2 GRE. Okay, 2 GRE, which is then equals to square root to 9.81, and then the radius of the earth, which is 6.4 times 10 to the power of 6. Okay, and then it is equals to 1.12 times 10 to the power of 4 ms negative 1. Now, of course, you can use the first equation because you are given the mass of the earth as well. Okay, you are given the mass of the earth, then you can apply the first equations. So first equations actually can be used at any position. That's why I say at any point in the outer space, okay, above the surface. And then for the second equation, it's just valid for on the earth. So questions B. Determine the kinetic energy of the rocket in part A that must have at the surface in order to move infinitely far away from the earth. So to move infinitely far away, it means it is to escape. Okay, it is to escape from the earth. So you have escape velocity, then you can calculate the escape kinetic energy. Okay, so K is equals to 1 over 2 mve squared, which is then equals to 1 over 2 the mass of the earth, which is a 6. No, not 6. So when it comes to this m, now you have a small letter m. Small letter m means you're going to look at the rocket. Okay, you're going to look at the rocket. So m is a 3000 kg. Okay, 3000. Kinetic energy is the object that is moving. Now the object that is moving is our rocket. So we use 3000 times the v squared. Okay, so we have the 1.12 times 10 to the power of 4 squared. So it is equals to 1.88 times 10 to the power of 11 joule. Okay, so this m, I'm going to make a remark here. This m belongs to object that is moving. Okay, therefore you cannot use M of the Earth because Earth is not moving. Earth, it doesn't want to escape from itself. All right, how can it escape from itself, right? Therefore, the thing that is going to move, that's going to escape from the Earth is the rocket. So we use M for rocket. Okay, M's of a rocket. So that is questions 1. All right, so now I give you now it's 36. I give you 4 minutes to write down the equations and also the answer. And of course, questions A, you can add in one more method. Okay, sendiri boleh catat lagi satu kaedah untuk jawab soalan A. So soalan A, you can use either equations to solve it. Okay, and then questions B, okay, make sure you use the right M, the correct M. So masalah yang biasanya pelajar ada, tak tahu cari R, tak tahu cari M. And then dapat semua salah. So bagi anda sampai 12.40 untuk buat catatan. All right. Okay. Now let's look at questions 2. Questions 2 is a slightly more complicated. Okay. So a projectile. Where is it? Okay. A projectile is fired vertically from the Earth's surface with an initial speed of 10 km per second square. Okay, 10 km per second. Okay, 10 km per second. Neglecting air resistance, how far above the surface of the Earth it goes? So what happens right now? Okay, let's sketch a diagram. Okay, let's sketch a diagram. So initially, now let's say this is your object. Okay, your object initially is located at the surface of the Earth. Okay, with an initial velocity u equals to 10 km per second. Okay. And now what you want to calculate, okay, the final position, is you want to calculate the h. Okay, you want to find out what is the h. So h is an unknown. All right, above the Earth, neglecting is how far. So this is your object, and then this is the Earth. So how are we going to calculate these questions? Okay, let us think. So now you have initial velocity, and then this is your final velocity. So how far above it goes? I mean, this is the maximum height, where v is equals to 0 ms negative 1. Okay, v is equals to 0 ms negative 1. And then we have the r of the Earth. Okay, we have the r. So what are we going to do right now? Let's see. Okay. So let's look at conservations of energy. So summations E initial equals to summations E final. So now we have a height and now we have kinetic energy. U initial plus U plus Q plus K initial equals to U final plus K final, right? U final plus K final. And then U initial, what is the U initials that we have? So we have, okay, now I'm going to leave U as an unknown first, okay? K initial, I have 10 km, so it's the non-zero value. But when it comes to K final, if you look at K final, it should be equals to 0. Okay, K final is equals to 0. Why? Because your V is equals to 0. So we're left with U initial plus K initial equals to U final. And then we rearrange the equations. K initial is then equals to U final minus U initial, which is our delta U. So K initial, now what do we want? Okay, we want 1 over 2 U square equals to, negative. Yeah. Negative GMM and then bracket. Now, initially it's located on the surface of the Earth. So 1 over, okay, we have capital letter R. Okay, so it wants a in final minus initial, 1 over R. The final is above a height, so plus H minus 1 over R. Okay, minus 1 over R. So plug in all of the value, okay, plug in the values that you have. So 1 over 2, now you have a M. So M is a 6. Now this M is the M's of the object that is moving. So do we have the M? No, we don't have M. But then what can we do? We can cancel it out. The small letter M. Okay, we can cancel out the small letter M because we have it on both sides. So it left with just U, which is 10 times 10 to the power of 3. Okay, 10,000. 10,000 km square equals to negative 6.67 times 10 to the power of negative 11 times with 6.4 times 10 to the power of 6. And then for the R, what am I going to do? So 1 over, now this one is a 6.4 times 10 to the power of 6 plus H minus 1 over, okay, 1 over R, which is a 6.4 times 10 to the power of 6. So done. If you look at these equations, we have just one unknown, which is the H. Okay, which is the H. So rearrange the equations, you will obtain H is equals to 2.55 times 10 to the power of 7 meter. Okay, so you have to rearrange step by step. Tengok macam mana kamu nak rearrange. That is more on mathematics. So this question is the crucial part is you have to know that energy is conserved. Okay, now you want to calculate the final velocity, so you use a final height, the maximum height. So you use v equals to 0. Okay, you use v is equals to 0. So u initial plus k initial equals to u final plus k final. So k final is equals to 0. And then k initial, we have the value, right? And then for the u, we also have the final and initials. And we want to find out what is the maximum height that it can reach. Okay, so that is how you solve it. So I give you 5 minutes to write it down. Okay, I give you 5 minutes to write it down. You try to calculate the value. See if you can get an answer or not. Oh yeah, for these questions, you cannot use MGH, yeah, because your final H is very far away from the surface of the Earth. MGH is only valid if your object is located very near to object surface, okay, very near to the Earth surface, sorry. So now your H is located at a point that is quite far away from the surface, therefore you cannot use MGH. Okay, so saya tahu ada yang akan pakai MGH sebab dia nampak macam soalan chapter 5. But in this chapter, your U it cannot be equals to your potential energy cannot be equals to MGH because the H is very far away. Okay, very far away from the surface of the Earth. So 5 minutes for you to write it down, including the diagram. Okay, make sure you sketch the diagram. So MGH U cannot be equals to MGH. Okay, so I think that is the last questions for today's class. So next class, we are going to spend 1 hours on discussing satellite. I hope 1 hours can finish all 4 questions. And then after that, we will spend some time on discussing the UPS questions. Okay, we're going to go through the UPS questions. And perhaps I'm going to finish chapter 8 as well. Okay, I will go through it quickly if we have the extra time. Because I need to finish chapter 8 until this week. Okay, because you will be receiving the assignment questions next week. So this week I need to finish until chapter 8 and then